opportunity which is not maybe even more important than a lot of the things we study in this class, and let me introduce you the more precise and formal definition of the very important notion of arithmetic groups. Arithmetic groups play an important role in mathematics in many areas like group theory, number theory, geometry, and more. So let K be, I will define it in a fairly general way. If you're not familiar with some of the notions, think about this, the spatial case. Let K be a global field. So by global field we mean either a finite K over Q is finite if this is characteristic 0, or K over the rational point if in characteristic P is a finite extension. And on such a field we have places valuations, Archimedean valuation or non-Archimedean valuation.
Completions.
What?
Completions. Completions.
Completion of valuation.
Topologies.
Topology, whatever, yeah. And let S be a finite set of valuations of K, always including all S infinity, which will be our notation for the Archimedean valuation. Archimedean, and OS, which is called the ring of S integers, is the set of all x in K such that V of x is greater or equal 0 for every V which is not in S. So the easiest examples to think about is that we take say K equal the rationals number. We take now S to be the infinity and the prime P. You know that valuations on the integers are in, you probably talked about that, right? We are. That valuations on the rational numbers are in one-to-one correspondence with the prime number except of the infinity.
No, I don't.
Okay, but okay, that's about the p-adic valuation anyway. The ring OS in this case is Z1 over P. This is a kind of an example you want to think about. If you know this language, fine. If you don't know, just think about something like that. Or if you take K to be FQ T, rational function over a finite field, then you can take FQ of T and again localize it divided by, say, T plus 1 or by every irreducible polynomial gives you such a valuation. You know, you can localize, sorry, it's not, this is with these brackets. You take the polynomial in T, that's the ring of integer, that's also, of course, maybe example 0 should be Z, and the 0 prime should be FQ, the full polynomial. But you can also localize them at finitely many primes. That's basically the whole issue. You take the ring of integers and you localize them at finitely many primes. That's all, nothing more fancy than that. Now let G be an algebraic group, a K-algebraic group. So what does it mean for us? It means that G, we always assume that it already comes with some embedding. One can talk about the abstract. G is a subgroup of GLN defined by polynomial with coefficients in K. So again, if you know what's this, if not, just think about G equal SLN. So what does it mean? You take the algebraic group defined by one polynomial, the determinant equal to 1. Or you can take G equal the symplectic group 2n, which means that you take all the matrices which satisfy, which preserve the alternating form. It's also defined by polynomial, right? I mean, you define some polynomial, or define J, T, A equal to A, anyway, A equal to J, right? Something like that. So it's all these defined by polynomial, and then we take gamma. This is the arithmetic group, or sometimes called S arithmetic group. Usually we just call it an arithmetic group. Will be, you see, there is a delicate point in which I'm kind of bypassing by assuming already that G is defined as a subgroup of G of N, and then I can talk about G of K. G of K means the K point of G. Union GLN of OS. And this is an S arithmetic group. Now, in general, this sits as a discrete subgroup inside the product over all V inside S of G KV. You all know it for the case of the integers, for example. The integers, if you look at GK, take SLN. So again, let's look at examples, like corresponding to example 0, we get, for example, gamma equal SLNZ, the integer point of SLN, or ST 2n over the integers, or gamma equal SLN Z 1 over P. So if we take SLN Z, then this is a discrete group in SLN R. If you take SLN Z 1 over P, it's a discrete group in SLN R cross SLN QP. But it's not discrete in each one of them, separately. Just like the ring Z1 over P is not discrete in R, it's not discrete in QP, but it's discrete in the product. If you take SLN Z1 over P, it's discrete in the product. This is a deeper theorem that it's also a lattice there, of finite covolume, but that's something we'll discuss later on. Now, we used some kind of a miracle which happened in the specific example that we took. We chose a specific algebraic group such that the G of R is compact. You are still discrete in the product, and because the G of R is compact, then you are kind of lucky, and the projection to the p-adic is still discrete. This is the specific lattice that we were working, and I'll come back to that. I just wanted to, for a minute, to give the general picture, because right after this specific example, not next week, as I said, in 2 weeks, then I will go and do it in a more general care. But now I really want to define. Now I just want to say that sometimes people call gamma, write it as GOS. One should be a bit careful about this notation. That's okay, we all do it, we all use it like that, but you have to be a bit careful because G of OS is not well defined. It's well defined after you fix this representation. But sometimes the same algebraic group can appear in different representation, and then G of OS can vary. It's not so, it's only up to, they're all commensurable, it's only up to finite index, but you have to be a bit careful. Anyway, I don't have time to even to stop for that. Now, if I is an ideal in OS, then I can define the kernel. I will define gamma I, the congruent subgroup gamma I. It's simply the kernel from I to GLN OS over I. By the way, in this case, if I is not 0, in this case, for rings like that, this is always a finite index, automatically. Every ideal in such...
I is prime?
What?
I is prime?
No. Every ideal. Every ideal is a finite index, like every ideal in Z is a finite index, every ideal in a polynomial ring is a finite index, so if you take also finite extension, even though in general they're not Euclidean or something, but still. Okay. And then, and therefore, gamma I is a finite index in gamma. Because if this ring is, this quotient ring is finite, this quotient ring is finite, so GLN of OS is a finite group, then the kernel from here to here is a finite index subgroup. So we have a finite index subgroup, and these are the congruent subgroups. These are the so-called congruent subgroups, which are, or sometimes called principal congruent subgroup. Congruent subgroup is everything containing such a group. The congruent subgroup. The famous congruent subgroup problem is not so relevant for us, but it asks whether every finite index subgroup of gamma contains something like that, gamma I. But there's something we just... Okay, now there is an important theorem which I will state it and I kind of explain it more by an example. This is called the strong approximation theorem, which the best way to state it is using Adels, etc., but I don't want to go to that. If G is semi-simple and simply connected, which, if you know what is it, fine. If you don't know, at least in characteristic 0, a quick definition, the group G is simply connected. If we look at G over the complex number, then it is simply connected as a topological space. But, for example, SLN Z is semi-simple and simply connected, but say PGLN, and that's relevant. I want to state it, and because there is something delicate which will come in the combinatorics later on. But GLN is semi-simple, but not simply connected, and we'll see that this is playing a role in a minute. Then, okay, here I'm a bit cheating. Then the map from gamma to GOS over I is onto. There is a bit cheating here. One should really talk about this because you see, gamma, as I said, is not really well defined in a precise way. As I said, it depends on the Z. So that's not really.
For every I?
Yeah, the point of the strong approximation is that it's true for every I. I will give you kind of an easy proof, easier proof, at least in some cases, that it's true for almost every. But it's really true for every if you take the appropriate definition. So that's not not true. I'm writing a theorem as stated, but basically, because basically true, and I don't have time. But let me take an example that will illustrate everything. I want to say that EG, and this is a true theorem, if you take SLN Z and you map it onto, say, SLN Z mod P, let's talk about that. This is onto. Let's see why. I mean, that's a nice exercise. What?
Generated by you.
Right. So by elementary matrix exercise, this is on to prove SLN FP, because it's a field, but it's also true for Z mod NZ, is generated by the elementary matrices. So I know that all the elementary matrices are obtained because I take elementary matrix, elementary matrix is just a matrix like 1, 1, 1, 1, and here and some, and 1 there, and everything else is 0. So those type of matrices already generated, they appear in the image. I want to give you a different proof for P8 that will be relevant later on, but the different proof will give you more. Let me give you something which is also part of the so-called strong approximation theorem for linear groups, not necessarily for arithmetic group. Here is a theorem. Basically, we prove it, but I'll do it very quickly because I'm doing here, I'm wasting my time here in order to save you time later on. Later on, I say the proof there, it's slightly more complicated, but it's exactly as the simple proof here. And the point is the following: let H be a subgroup of SL2Z. You know, SL2Z, I hope everyone knows, is essentially a free group, right? It's a subgroup. It has a subgroup of finite index which is free. Okay? Which is such that H is not virtually a billion. So it's not finite or not cyclic or something like that. But it can be also, but H can be of infinite index. Then, for all large primes, Q, the map H to SL2Q is onto. Certainly, I cannot say that it's onto for every, because I can take H to be the kernel from SL2Z to SL2Q. But I claim it for almost. And the proof we can assume H is non-abelian free group, because I can move to a smaller group, like the SLNZ is a subgroup which has a free subgroup of finite index. So if I take H, a subgroup of SLNZ, it also has a free subgroup of finite index, because a subgroup of a free is a free. So I just intersect it with a free group. And because I assume it's non-abelian, then this subgroup of finite index is really free, honest free, namely non-abelian free group. So, and I can go to a even smaller group and assume it's free. Now, here is a fact which is not so difficult. Every subgroup of SL2Q is either meta-abelian. Meta-abelian means that it's an abelian by abelian group, which means that it's something like that. If you look at the upper triangular matrices, the upper triangular matrices in the 2 by 2 matrix is a meta-abelian group. There's a subgroup of, you look at the unipotent subgroup, it's a normal subgroup, you divide it by the normal subgroup, you get the diagonal, which is abelian. So it's abelian by abelian, right? Is it clear? Please stop me, because I'm not sure what's the experience of people here.
You mean that the second commutator vanishes?
The second commutator vanishes, right? The commutator will come, yeah. Okay, there's another way. If you take two upper triangular matrices, then their commutator is one on the diagonal and something there, and this something there is an abelian group, so second commutator always vanishes. Or a subgroup of A5. There are very few subgroups to SL2Q. Either meta-abelian, or they are of order at most 60 and really can be embedded in A5. Now it means, therefore, there exists a world W in, say, 4 generators, but I mean, you can do it there, such that X, Y, Z, U, such that if, for example, take the following world. Take W of X, Y, Z, U be the commutator of XY, commutator with ZU, and then to the order 60. This is a non-trivial word in the free group on 4 generators. Well, I can assume that H is a free group on 4 generators, because every free group on whatever number of generators contain a free group on 4 generators, so I can really go even further. So this is a non-trivial in H, such that if pi from H, so let's say that H is really the free group on X, Y, Z, and U. 2, if SL2Q is not on 2, then pi of this W must be the identity. Because if the map from the group H is not on 2, SL2Q, then we are inside a subgroup of SL2Q, a proper subgroup. Well, I have to say, of course, every proper subgroup. Of course, the group SL2Q is a simple group, or almost a simple group. It's not meta-abelian and it's not inside A5. I meant every proper. So if the image is not everything, then it must be smaller. Smaller means either meta-abelian or of order 60. So if I'm inside the proper group, then the image of X, Y, Z, and W are inside the proper group, and then I take commutator if this, oh, I have to take here, no, I took commutator. I take, then if it's meta-abelian, the commutator of them of trivial. If it's not meta-abelian, it's order 60, so I'm getting something of here of order to the 60, then it must be trivial. And now, if G, if any word in SLNZ satisfy pi Q of W is E for infinitely many Q's, then G must be the identity. Right? If you have a matrix which is congruent to the identity matrix modulo infinitely many prime, then it must be the identity. So what does it mean? That we got to a contradiction. Because W as an element of G, as an element of H, is non-trivial. Right? And suddenly we found out that for infinitely many primes, it is trivial. Okay.
So what is the conclusion?
What? What would you say?
What is the conclusion of this break that we...
So this is a contradiction, because you see, I want to prove that pi Q is onto for almost every Q. If not, then there exists infinitely many Q's for which this is not onto. But if it's not onto, then the image of this specific W as an element of the free group will be trivial. Are you all with me, or I lost you? Please ask. I have an element. You have to think of H on one end as a subgroup of SL2Z, on the other end as a free group. A free group, say, on 4 generators: X, Y, Z, and U. And on one end, I say that if pi is not onto, for infinitely many Q's, right? For every Q I have such pi of Q from H to SL and Q. If this is not onto, then it goes to a proper group. This proper group is either meta-abelian or for order 60, and in any case, the specific element W will go to the identity. If it goes to the identity for infinitely many primes Q, then it is the identity, but it's not the identity as an element of H, and therefore as an element of SL2Z. It is a contradiction, and therefore we deduce that pi Q is onto for almost every prime. Okay. But now I want to take a step here and to analyze carefully the non-simply connected case to show you that this is not true for PGL2. That's something which is a bit confusing, so let's do it carefully, because in the combinatorial applications it will be a crucial point. So I want to start with something which is somewhat easy. Let's look now at PGL2Z. Okay, we can argue even what we mean by that. What is PGL? But let's not be too sophisticated. And PGL2Z means this is GL2Z divided by its center. The center is plus or minus the identity. Now we have a map from PGL2Z to PGL2FQ Q prime. The full group, not talking even about that. The question is this onto or not? Okay, let's understand first of all the group. What is PGL? What is PGL2FQ? Well, this is GL2FQ divided by its center, but let's be careful. The center here is all the matrices Ti, where T is in FQ star, right? First claim that P, and let's compare it to the group PSL2 FQ. What is PSL2 FQ? Is SL2 FQ divided by the center. But what is the center of SL2? In SL2, there is a very little center, right? It's only plus or minus 1. But you see, let's be careful here. The group SL2 inside GL2 is of index, what's the index here? Q minus 1, right? SL2 is the kernel of the determinant map, right? And the determinant map takes GL2 to the field, FQ star, so the index. When we drop it down, here we divide by something of order Q minus 1. Here we divide by something of order 2. Right? The total index before that was Q minus 1. So from this, you can see either by the computation or by, which I want to show you by the size, the index here is exactly 2. Always, for every Q. Okay. The exercise is compute. This is slightly easier than the general case. What is PGLN FQ? over PSLN. PSLN. That's a good exercise, which I will not tell you what's the answer. But think about it.
Q.
What?
Q is the top line.
Ah, okay. Yeah, I have to go here. Okay. Here? Yeah, okay. Q. Fine. Yeah. Yeah, I don't want to worry about it. Go on. Maybe. Okay. Now, what's the story? Why this is, okay, now, time is running, so let's now take GL2Z and see what happened. We map from GL2Z to GL2FQ. This is certainly not onto, because the matrices here have determinant either plus or minus 1. And here, the determinant could be any invertible element of FQ. So this is not onto. That's not an issue at all. The question is, what happened after I would go to PGL2Q? Then, the map from here to here, if I take the full map from here to here, right? Now I want to discuss and check, is it onto or not? Now, let's see. If I will start here with SL2Z, SL2Z to SL2FQ is onto. Right? That's what we said before. For every Q, because this is just the elementary matrices argument. And this goes from here is onto. So there is no question. So there is no question, and this is onto. Of course, that's by definition. So there is no question that the image, so the image of PGL2Z inside PGL2Q certainly contains PSL2, which is an index 2 subgroup. The only question is whether it's everything or just subgroup of index 2. Maybe it's inside. So if I will show you one matrix outside PSL2, which is in the image, then we are done. So, and in fact, so the image from PGL2Z to PGL2Q is onto, really, if and only if take a matrix, what's the story? We take a matrix like, look at the following matrix, -1, 0, 0, 1. Let's call it T0. Now this matrix is in the image of GL2Z. Right? Now GL2Z is equal SL2Z union SL2Z times T0. Right? I mean, SL2Z is of index 2 in GL2Z, and if I choose a matrix which is outside in the coset, then the group is there. Okay, let's see what happens when we go to GL2 FP. Then what I'm getting that the GL2, let's denote it plus minus, or maybe I call it SL2 plus minus Q. When I write a plus minus 1, I mean the matrices of determinant plus or minus 1 in SL2Q. This is still the same as SL2Q union SL2Q times T0. This time I think of T0 as the matrix of GL2, Q. Right? The matrix of determinant minus 1 plus or minus 1 contains SL2 as a subgroup of index 2, and therefore it is this subgroup plus 1 coset. Now what happens when I drop down modulo the center? So there is just one issue. What's the image of T0? Is now look modulo the center of GL2Q. What happened to T0 modulo the center of GL2Q? Is it, so I claim, T0, so the question is, claim, there exists A in SL2Q such that pi, maybe I want to call it pi, phi of A T0, phi of A T0 equal to phi of A in PGL2Q, if and only if Q is congruent to 1 mod 4. So, okay, let's go with first and then you'll see what's the corollary. What does it mean? What I need here? I need a matrix in SL2 such that they have the same image. But phi is the map from GL2Q to PGL2Q. Okay? Now, phi of A equal phi of T naught if and only if there exists an element in the center of GL2Q, Z, we'll write it as ZZ00, such that A times Z equal, or maybe A equal T times Z, right? When two elements have the same image, if one is obtained from the other by an element of the kernel, which means that the determinant of A is equal to the determinant of T0 times Z, but this is the determinant of T0 times, which is minus 1 times the determinant of Z, and this is equal to minus 1 times Z squared. And this is 1. Now, which means if I can solve this equation, if I can solve this equation that minus 1 times Z squared equal 1, if I can find such a Z, then I can arrange that T0 times Z will have determinant 1. And as it's well known, so I have to solve Z squared equal minus 1. And this as a solution, if and only if Q is congruent to 1 mod 4. So what is now the corollary? The corollary is, but you see what happened, if Q is congruent to 1 mod 4, there exists a matrix in SL2 with the same image as T node, which means that all these collapse. It means that all this, the image here which goes to here, when we go to PGL, it's inside PSL. So the corollary is that if Q is congruent to 1 mod 4, then the image of GL2Z inside PGL2Q is equal to PSL2Q, and it's not onto. But if Q is congruent to 3 mod 4, then GL2Z to, sorry, we can talk about PGL, right? Because the map from PGL, from GL to Z here, splits anyway to the center. And I wanted really to study the group PGL2. So the map to PGL2Q is on 2. So you see that we have strong approximation, what we call the strong approximation theorem, is not true for the group PGL2. It's true for SN2, but PGL2, which is not simply connected, it's not true, but it's almost true. I mean, it failed from infinitely many primes, but it's not fails in a strong way. We really can understand what is the image. And the image is just a sample of index 2 in PGL of the finite field, which is not too bad, but this not too bad thing is going to play an important role for us. I guess this is a good point to start. Very difficult to manage to finish all what I need to finish. Okay, let's see. Okay, let's stop here.